There's something undeniably thrilling about looking up at the night sky and realizing just how little we truly understand. The universe isn't just vast, it's packed with mysteries so bizarre, so utterly inexplicable, that even the brightest minds in astrophysics are left scratching their heads. What if I told you there are cosmic events defying every law of physics we've ever known? Phenomena so strange they seem ripped straight from science fiction, yet they're happening right now in the depths of space with no clear explanation in sight. That's the reality we're diving into today, a journey through 30 of the most mind-bending, spine-tingling enigmas lurking in our galaxy and beyond. Think about this for a second. We've mapped entire continents, decoded the human genome, and sent probes to the edge of our solar system. Yet out there, in the infinite black, there are forces at work that challenge everything we thought we knew. Stars that vanish without a trace, galaxies spinning in ways that shouldn't be possible, signals from the void that repeat with eerie precision as if something or someone is trying to get our attention. These aren't just curiosities, they're gaping holes in our understanding of reality itself, and the deeper we look, the more questions we uncover. That's why this exploration isn't just about listing strange phenomena, it's about stepping into the unknown, where every discovery feels like uncovering a piece of a puzzle we didn't even know existed. By the time we're done, you'll see the cosmos in a whole new light. Some of these mysteries might keep you up at night. Others might make you question whether we're alone in the universe. But one thing's for certain, you're about to witness the most astonishing, unexplainable wonders space has to offer. So buckle up, we're heading into the great beyond, where the rules of science as we know them don't always apply. It started as just another quiet night at Ohio State University's Big Ear Radio Telescope, August 15, 1977. The machine was scanning the cosmos as it always did, listening to the faint whispers of the universe until suddenly, it wasn't a whisper anymore. For 72 seconds, a signal burst through the static so powerful, so unmistakably artificial in nature, that astronomer Jerry Ryman nearly fell out of his chair. He circled the alphanumeric code on the printout in red pen, scribbling one word beside it. Wow! That single word would go down in history. The numbers told the story. The signal was 30 times louder than background noise, narrowly focused, and broadcasting at exactly 1420 megahertz, a frequency scientists had predicted might be used by extraterrestrial civilizations. Even stranger, it came from the direction of Sagittarius, a star cluster with no known planets at the time, and then just like that, it vanished, no repeats. No echoes, not a single blip in the 40 years of searching since. So what was it? One theory points to a pair of comets passing through that region, their hydrogen clouds possibly mimicking the signal. But here's the catch, those comets weren't even discovered until 2016, and their trajectories don't fully explain the data. Others argue it could have been a military transmission or satellite glitch, yet nothing matches the signal's unique fingerprint. Then, of course, there's the electrifying possibility, the one that sends chills down your spine that we weren't alone in hearing it, that something or someone was deliberately broadcasting just long enough to make us wonder. The truth we may never know, but that's the haunting beauty of the wow signal. In a universe that's overwhelmingly silent, it was a fleeting shout into the void, one that still echoes in the minds of anyone who's ever looked up and dared to ask, are we listening closely enough? Imagine holding a flashlight in a pitch-black room, shining it around only to realize you can't see most of what's actually there. That's essentially what we're doing when we study the universe with telescopes. Because here's the unsettling truth. Everything we've ever observed, every star, planet, and galaxy accounts for less than 5% of what actually exists. The rest, a ghostly presence called dark matter, making up 27% of the cosmos. It doesn't emit light, it doesn't absorb or reflect it. But we know it's there because without its gravitational pull, galaxies would literally fly apart. Take our own Milky Way. The stars at its outer edges are orbiting so fast that centrifugal force should have flung them into intergalactic space long ago. The only reason they haven't, an invisible scaffold of dark matter, its gravity acting like cosmic glue holding everything together. We've even mapped its distribution by watching how it bends light from distant galaxies, a phenomenon called gravitational lensing. These eerie, warped images are like seeing the silhouette of something we'll never directly observe. So what could it be? The leading candidates sound like something from a particle physicist's fever dream. WIMP, weakly interacting massive particles, hypothetical heavy particles that barely interact with normal matter except through gravity. Then there are actions, ultra-light particles that might have formed in the seething chaos just after the Big Bang. Underground labs have spent decades hunting for these phantoms with detectors chilled to near absolute zero, waiting for a single telltale vibration. But so far, silence. Here's where things get truly bizarre. Some theorists argue we might be going about this all wrong. What if dark matter isn't a particle at all, but a flaw in our understanding of gravity itself? Modified Newtonian dynamics, or MUND, suggests Einstein's equations might need tweaking at cosmic scales. Yet even this radical idea can't explain all the observations, leaving us with a cosmic riddle that keeps rewriting the rules. Every failed detection, every dead end in this 80-year search only deepens the mystery. Because dark matter isn't just some academic curiosity, it's the hidden architecture of reality, the unseen hand shaping everything from the birth of galaxies to the fate of the universe itself. And until we solve it, we're like astronomers staring at shadows on a cave wall, trying to comprehend the fire casting them from light years away. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine pushing everything apart at an ever-increasing speed. Picture blowing up a balloon with dots on its surface. Now imagine that balloon inflates faster and faster without you adding more air. That's essentially what dark energy is doing to our cosmos, stretching space itself in ways that defy all expectations. The discovery came in 1998 when two teams studying distant supernova made an unsettling observation. These exploding stars, used as cosmic measuring sticks, were dimmer than they should have been. The only explanation, the space between us and them had stretched more than predicted, meaning the universe wasn't just expanding, but accelerating. It was like tossing a ball in the air only to watch it shoot away faster instead of falling back down. This revelation flipped cosmology on its head, earning the researchers a Nobel Prize and leaving scientists scrambling to explain how 70% of reality could be made of something they'd never accounted for. Unlike dark matter's gravitational pull, dark energy appears to be a property of empty space itself, a repulsive force Einstein once theorized as his greatest blunder. His cosmological constant, originally introduced to keep the universe static, now ironically describes its runaway expansion. Yet even this explanation feels incomplete. Some models suggest dark energy might weaken or strengthen over time, potentially leading to a big rip where galaxies, stars, and even atoms are torn apart. Others propose bizarre quantum effects, where virtual particles flickering in and out of existence somehow push space outward, the most unsettling part. We have no way to directly detect it. While dark matter reveals itself through gravity's grip, dark energy leaves no fingerprints, just its accelerating footprint on the fabric of reality. Future telescopes may analyze millions of supernovae for clues, or perhaps uncover flaws in Einstein's equations. Until then, we're left staring at a cosmos where the dominant force remains utterly alien, its secrets written in the expanding darkness between the stars. One moment, the cosmic radio waves are silent. The next, an eruption so powerful it outshines entire galaxies for mere milliseconds. These are fast radio bursts, or FRB, some of the most explosive and mysterious events in the universe. Lasting barely the blink of an eye, these bursts pack more energy than the Sun emits in 80 years, and the strangest part, we still have no idea what's causing them. The first FRB was spotted in 2007, hidden in archival data from the Parkes Radio Telescope in Australia. At first, astronomers dismissed it as an instrument glitch until more began appearing across the sky. Their randomness makes them nearly impossible to predict, flashing once and vanishing without a trace. Except that is, for one, FRB 121102 is the cosmic rebel that broke all the rules. Unlike its one-and-done counterparts, this burst near a dwarf galaxy 3 billion light-years away has repeated dozens of times, firing off signals in erratic but detectable patterns. It's as if the universe left us a voicemail, one that keeps playing on loop. So what could possibly generate such titanic energy? Theories range from the plausible to the downright surreal. Magnetars, neutron stars with magnetic fields a trillion times stronger than Earth's, are prime suspects. Picture a starquake where the crust of a magnetar snaps like a rubber band stretched too far, releasing shockwaves of radiation. Yet even these cosmic powerhouses might not explain the sheer intensity of the most extreme bursts. Then there's the wildcard hypothesis, collapsing alien megastructures. Imagine a civilization building a Dyson sphere, a colossal energy-harvesting shell around a star, only for it to catastrophically fail, unleashing a burst detectable across the universe. While it's a tantalizing thought, most scientists lean toward natural explanations, however exotic. One thing's certain: the fact that these bursts travel billions of light-years to reach us means they're relics of an ancient universe, their light carrying secrets from a time when galaxies were just beginning to form. The real enigma, distance itself, adds another layer of strangeness. As FRBs race through the cosmos, they pass through clouds of ionized gas, scattering their radio waves like sunlight through a prism. By measuring this scatter, astronomers can map the universe's missing matter, the diffuse atoms hiding in the voids between galaxies. It's as if these mysterious flashes are doing double duty, baffling us with their origins while acting as cosmic lighthouses, illuminating the invisible structure of everything. Every new detection raises more questions than answers. Why do some repeat while others vanish? How can something so brief unleash such staggering energy? With every unanswered puzzle, FRBs remind us that the universe still holds phenomena beyond our wildest imagination, flaring up in the darkness, just long enough to remind us how much we have left to discover. Picture the Milky Way as a ship sailing through space, only instead of drifting aimlessly, it's being pulled toward an invisible harbor with unimaginable force. This is the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxies, including our own, toward it at over 2 million kilometers per hour. The strangest part, we can't even see what's doing the pulling. Hidden behind the Milky Way's dense star fields and cosmic dust in the constellation Norma lies what astronomers call the zone of avoidance, a region so obscured by our own galaxy's bulk that it's like trying to peer through a fogged-up windshield. For decades, this blind spot kept the Great Attractor's true nature a mystery. Early X-ray and radio surveys hinted at something massive, perhaps a supercluster of galaxies with the combined heft of tens of thousands of Milky Ways. But the numbers didn't quite add up. The force required to tug galaxies across such distances seemed too great, even for a structure that size. Then came an even more startling revelation. The Great Attractor itself might not be the final destination, but just a waypoint on a far grander cosmic journey. Beyond it lies the Shapley supercluster, the most massive concentration of galaxies in our local universe. Some scientists argue this colossal structure, over 650 million light-years away, could be the true source of the pull. Yet others speculate there's something even more exotic at work, a concentration of dark matter so dense it warps the fabric of space-time like a hidden whirlpool. Recent infrared surveys have peeled back the zone of avoidance's veil slightly, revealing a chaotic scene of colliding galaxy clusters and swirling hot gas. But the Great Attractor's core remains elusive, its true scale and composition still debated. One theory suggests it's not a single object, but a gravitational knot where multiple cosmic filaments intersect, a crossroads of the universe's large-scale structure. What's undeniable is that this enigmatic force has rewritten our understanding of cosmic motion. Galaxies aren't just drifting apart from the Big Bang's aftermath, they're also marching in formation toward unseen giants, caught in a celestial tug of war we're only beginning to map. Every new observation deepens the mystery, hinting that the universe's greatest puppet master might still be waiting in the shadows just out of sight. Out of the hundreds of thousands of stars monitored by the Kepler Space Telescope, one stood out like a cosmic glitch in the system. KIC 8462852, better known as Tabby Star, doesn't behave like anything else we've ever seen. Imagine a light bulb flickering unpredictably, sometimes dimming by just 1%, other times plunging by a staggering 22% before snapping back to normal. Now picture that light bulb is a distant sun over 1,400 light-years away, and those dips in brightness last for days, even months at a time. That's the jaw-dropping anomaly astronomers have been scrambling to explain since its discovery in 2015. Most stars experience regular, slight dimming when planets pass in front of them, but Tabby Star defies all known planetary physics. Its dips are erratic, asymmetrical, and far too dramatic. The first instinct was to blame a swarm of comets, hundreds of thousands of them, blocking the light in clumps. But even that theory strains credibility. For comets to create such extreme dimming, they'd need to be impossibly massive or unnaturally clustered. Then there's the star's long-term dimming. Over a century of historical observations show it's faded by nearly 20%, something no natural stellar process should cause. Enter the most tantalizing and controversial hypothesis: alien megastructures. The idea hinges on a Dyson sphere, a hypothetical shell built around a star to harvest its energy. Broken segments of such a structure could explain the irregular light patterns, like clouds of solar panels passing in front of the star. Even mainstream astronomers admit reluctantly that while it's unlikely, it's not impossible. But the plot thickens. Dust eventually became the leading suspect when follow-up observations caught the star's light polarizing, a telltale sign of tiny particles scattering the light. Yet the dust doesn't behave normally either. It's not evenly distributed, and its composition doesn't match typical interstellar debris. Perhaps the most unsettling aspect isn't the star's strangeness, but our inability to categorize it. Every time a new theory emerges colliding planets, rogue black holes, even a distorted star shape, the data throws another curveball. Tabby Star refuses to fit into any cosmic box we try to put it in. It's a cosmic Rorschach test, revealing more about our own assumptions than the truth behind its flickering light. And that's precisely why it captivates us, not just as a scientific puzzle, but as a humbling reminder that even with all our tools and knowledge, the universe still holds cards it hasn't shown us yet. The universe isn't just expanding, it's a battlefield where the biggest galaxies devour the smallest in a silent, slow-motion feast. Galactic cannibalism sounds like something from a cosmic horror story, but it's a reality playing out in nearly every corner of the cosmos. Take the Milky Way, for example. Right now, it's in the process of tearing apart the Sagittarius dwarf spheroidal galaxy, stretching it into a shimmering river of stars that wraps around our own like a celestial serpent. These stellar streams, remnants of digested galaxies, are the ghostly fingerprints of collisions that unfolded over billions of years. But why does this happen? Gravity is the ultimate puppeteer. When a smaller galaxy drifts too close to a larger one, tidal forces like the difference in the moon's pull on Earth's oceans start ripping it apart. Stars are stripped away, forming long, luminous tendrils that orbit their captor. The most dramatic example, the Canis Major overdensity, a shredded dwarf galaxy whose stars now swirl through the Milky Way's outer halo. Even our neighbor, Andromeda, bears the scars of its appetite, surrounded by a graveyard of at least a dozen devoured galaxies. Now, shift your gaze 300 million light-years away to a sight that defies all expectations, Hoag's object. This enigmatic galaxy floats in space like a perfect cosmic bullseye, a dazzling golden core encircled by a pristine ring of young blue stars with nothing but darkness in between. Most ring galaxies form through violent collisions, where a smaller galaxy punches through a larger one's center, triggering star formation in a shockwave-like ring. But Hoag's object shows no signs of such trauma, no debris, no distorted core, just an eerily symmetrical ring that seems to have materialized out of nowhere. Theories abound, from gravitational instabilities to rare resonances between stars and dark matter. Some suggest a long-ago collision so perfectly aligned that all evidence has since faded, leaving only this perfect ring as a cosmic fossil. Others propose a phenomenon called secular evolution, where the galaxy's own internal dynamics somehow sculpted this flawless structure over eons. What makes Hoag's object even stranger is the presence of another, fainter ring galaxy floating in the distance behind it, a cosmic doppelganger that deepens the mystery. These two phenomena, one brutal, the other bewildering, show just how dynamic and unpredictable galactic evolution can be. One reveals the violent destiny awaiting smaller galaxies in a universe ruled by gravity, while the other stands as a testament to the fact that even after decades of observation, we're still stumbling upon cosmic oddities that rewrite the rules. Whether it's the remnants of a galactic meal or a ringed enigma floating in isolation, these structures remind us that in the grand tapestry of the universe, some threads are still dangling, waiting to be woven into the larger picture. The universe is unimaginably vast, 2 trillion galaxies, each with billions of stars, many hosting planets in habitable zones. Given those numbers, the math suggests civilizations should be everywhere. So where is everyone? That's the Fermi Paradox in a nutshell, the glaring contradiction between the high probability of extraterrestrial life and the eerie silence that greets us when we listen. Named after physicist Enrico Fermi, who famously asked, "Where are they?" during a lunchtime debate in 1950, this paradox has spawned theories ranging from the sobering to the spine-chilling. Let's start with the Great Filter, a bottleneck so catastrophic that it wipes out civilizations before they can colonize the galaxy, the terrifying possibility. We might be on the wrong side of it. If life frequently emerges but rarely progresses beyond a certain point, whether from self-destruction, think nuclear war, or unchecked AI, or natural disasters, gamma-ray bursts, supervolcanoes, then humanity's survival could be a cosmic fluke. Alternatively, the filter might still lie ahead, a looming existential threat we haven't encountered yet. Either way, the implications are haunting. We might be alone not because life is rare, but because intelligence is a dead end. Then there's the zoo hypothesis, the idea that advanced civilizations are deliberately avoiding contact, observing us like animals in a galactic nature preserve. It's a modern twist on the Prime Directive from Star Trek, suggesting we're being quarantined until we reach a certain level of maturity. But why? Perhaps to avoid cultural contamination, or worse, to prevent a less developed species from stumbling upon dangerous technologies. The darker version, we're not a zoo but livestock, and Earth is just another resource to be harvested when the time is right. But silence might have simpler explanations. Maybe we're listening wrong. Radio signals degrade over interstellar distances, and advanced civilizations could have moved beyond primitive communication methods, using neutrino beams or quantum entanglement instead. Or consider the timescale. Civilizations might rise and fall in mere millennia, leaving narrow windows for overlap. Imagine two people whispering in a vast desert, miles apart, never hearing each other. The most unsettling answer, though, is that we're truly alone, not just in our galaxy, but in the observable universe. That Earth is a 1 in a trillion fluke, and the cosmos is nothing but a beautiful, empty graveyard. Whether the paradox stems from filters, zookeepers, or sheer bad luck, one thing's clear: the silence isn't just a puzzle. It's a mirror forcing us to confront our own fragility and the precious rarity of a world like ours. Black holes aren't just cosmic vacuum cleaners, they're existential paradoxes wrapped in event horizons. Here's the problem. According to Einstein's general relativity, anything that crosses a black hole's point of no return is gone forever, crushed into the singularity. But quantum mechanics insists that information, the fundamental blueprint of every particle, can never be destroyed. So what happens when these two pillars of physics collide head-on? You get the black hole information paradox, a puzzle so profound it split the physics community for decades. The controversy ignited in 1974 when Stephen Hawking made a startling prediction. Black holes, he showed, aren't completely black. They emit radiation now called Hawking radiation, slowly leaking energy and shrinking over time until they vanish entirely. But here's the catch: this radiation appears totally random, carrying no trace of the original material that fell in. It's like burning a book and claiming the ashes contain no information about its contents. If true, this violates quantum mechanics' sacred principle of unitarity, which states information must always be preserved. The implications are staggering. It would mean the universe has an undo button, erasing its own history. Enter the firewall hypothesis, a desperate solution that feels more like science fiction. Imagine falling toward a black hole's event horizon, expecting to pass through smoothly, only to hit a seething wall of high-energy particles that vaporize you instantly. This brutal idea emerged when physicists realized quantum entanglement. The spooky action at a distance, linking particles, might break down at the horizon, releasing enough energy to create a deadly barrier. But critics argue firewalls violate relativity's core tenet. Free-fall observers should feel nothing unusual crossing the horizon. It's like saying every elevator's floor turns into lava the moment it starts moving. Clearly absurd, yet the math allows it. Another way out, the holographic principle. Picture a black hole's entire three-dimensional content smeared across its two-dimensional surface, like a cosmic DVD encoding everything inside it on the outside. When the hole evaporates, that information isn't lost, it's imprinted in the Hawking radiation, albeit in a scrambled form we can't yet decode. It's as if the universe stores backups on a hidden hard drive we're just beginning to detect. The stakes couldn't be higher. If information truly disappears, we'd need to rewrite quantum theory. If it's preserved, general relativity might need an overhaul. Every new observation, like the faint echoes of gravitational waves from colliding black holes, could hold clues. This isn't just academic nitpicking. It's a battle for the soul of physics itself, where the outcome could redefine reality's very fabric. And at the center of it all lies a simple, haunting question. In a universe built on information, can anything ever truly be lost? In the grand cosmic web where galaxies cluster like glittering cities, there's a place so empty it defies comprehension, the Boötes void. Imagine a sphere of darkness 330 million light-years wide, so vast you could fit 60 Milky Ways end to end across it, and yet it contains barely a handful of galaxies. This isn't just a quiet corner of the universe, it's a desert on a scale that challenges our understanding of how matter is distributed across space. Discovered in 1981 by astronomer Robert Kirshner and his team, the Boötes void, nicknamed the Great Nothing, shouldn't exist according to standard cosmological models. The Big Bang's afterglow, the cosmic microwave background, shows a universe that's remarkably uniform, with matter spread like a finely textured fabric. Yet here's a region where that fabric has a gaping hole. Statistically, such a void would require a 1 in a million fluke in the distribution of matter. So is it just a cosmic coincidence, or could something far stranger be at work? One radical theory suggests quantum tunneling in the early universe might be to blame. Picture the infant cosmos as a seething quantum foam, where space itself bubbled with unstable energy fields. If one of these bubbles collapsed into a lower energy state, it could have created an expanding pocket of emptiness like a phantom zone carved out by physics we don't yet understand. Others propose the void is evidence of a collision with a parallel universe, a bruise left by a brain-world impact in string theory's higher dimensions. But the truth might be simpler, if no less unsettling. Recent surveys have found slightly more galaxies in the void than originally thought, around 60 instead of the initial count of just a few dozen. Still, that's a fraction of what should be there. Some astronomers argue the void isn't entirely empty, but a vast, underdense region where galaxies are strung along invisible filaments, like sparse towns connected by lonely highways. Even so, its existence forces us to reconsider how structure forms in the cosmos. Could dark energy be pushing matter apart in certain regions faster than we thought? Or is the void a glimpse of an older, quieter universe, a relic from a time before galaxies filled the sky? The Boötes void doesn't just defy expectations, it taunts us. A cosmic blank spot on a map we thought we knew, whispering that even in our most detailed simulations of the universe, there are still places where the rules might be different. Whether it's a statistical oddity, a sign of new physics, or something even more profound, one thing's clear. In a universe teeming with light and motion, the great nothing reminds us that emptiness, too, can be a mystery worth unraveling. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1980s, they carried humanity's first messages to the star's gold plaques depicting our location in the cosmos. But these intrepid probes had another, unintended message for scientists back home. Something was wrong with their trajectory. Despite meticulous calculations, both pioneers were slowing down ever so slightly, as if an invisible hand were tugging them back toward the sun. This tiny deviation, just 300 nanometers per second squared, equivalent to the weight of a grain of sand pressing on your hand, sparked one of the most perplexing orbital mysteries of the space age, the Pioneer anomaly. For decades, this drift defied explanation. Was it a flaw in our understanding of gravity? Some speculated that Newton's laws might break down at extreme distances, or that dark matter's gravitational pull was subtly altering the probe's path. Others proposed exotic physics, like modifications to Einstein's general relativity, or even the influence of higher dimensions. The anomaly became a cosmic thorn in the side of physicists, a discrepancy too small to ignore yet too elusive to pin down. Then came the breakthrough: heat, not from some external force but from the probes themselves. Pioneer's nuclear power sources generated warmth, which radiated unevenly off the spacecraft's asymmetrical bodies. Every time a photon of heat bounced off the back of a dish-shaped antenna, it gave the craft a minuscule push backward, like a car slowing down because someone inside keeps throwing tennis balls at the windshield. By 2012, painstaking analysis of archival data confirmed thermal radiation pressure accounted for most of the deceleration. Case closed. Not quite. While thermal effects explain the bulk of the anomaly, some researchers argue lingering gaps remain. The heat model doesn't perfectly match the observed deceleration, leaving a tiny fraction unaccounted for. Could there still be an undiscovered force at play, or might it simply be instrument error lost in the noise of decades-old telemetry? The Pioneer's thrusters, used for occasional course corrections, also expelled minute amounts of gas, another potential factor. Yet even these explanations feel incomplete, like trying to balance a checkbook where the numbers stubbornly refuse to add up. What makes the Pioneer anomaly so fascinating isn't just the mystery itself, but what it reveals about how science grapples with the unknown. Here was a phenomenon so subtle it took years to detect, yet profound enough to challenge our trust in physics itself. It's a reminder that even in the era of gravitational wave detectors and quantum computers, the universe still hides secrets in the details, tiny discrepancies that might one day lead to monumental discoveries. The pioneers may have solved their own riddle, but their legacy endures as a testament to the power of curiosity. Sometimes the smallest anomalies point to the biggest questions. The cosmic microwave background, the afterglow of the Big Bang, should be the ultimate tabula rasa, a perfectly random snapshot of the infant universe's heat. But when scientists mapped its subtle temperature fluctuations, they stumbled upon something so unsettling it earned a name straight from a conspiracy thriller, the axis of evil. This isn't some abstract cosmic quirk, it's a spine-tingling alignment between the CMB's largest scale patterns and our own solar system's ecliptic plane. In a universe that's supposed to be isotropic, where no direction holds special significance, this is like finding the universe's wallpaper perfectly matched to the tilt of your backyard gazebo. The discovery emerged from painstaking analyses of NAS, a Wilkinson microwave anisotropy probe, and later the Planck satellite. These missions mapped the CMB's temperature variations, tiny ripples representing density fluctuations from the universe's first moments. Statistically, these ripples should point anywhere with equal probability, like confetti scattered randomly across a floor. Yet the data showed an eerie preference. The CMB's quadrupole and octupole moment, its largest scale fluctuations, aligned suspiciously well with our solar system's orientation. The odds of this happening by chance, less than 1 in 100. Skeptics argue it could be systematic error, some unnoticed artifact of how we process the data, or even contamination from our galaxy's dust. Yet repeated analyses, including a 2017 study filtering out all known local influences, found the alignment persisted. Another camp suggests the anomaly might trace back to cosmic inflation, the universe's exponential expansion in its first fraction of a second. If inflation wasn't perfectly uniform, it could have imprinted a preferred direction on spacetime itself, like stretching taffy that retains hidden wrinkles. Then there's the most radical interpretation. We're seeing evidence of a pre-Big Bang universe. Some theories propose our cosmos is one bubble in an infinite multiverse, and the axis marks where our bubble brushed against another, leaving a fingerprint in the CMB. Others speculate about a fundamental asymmetry in the laws of physics, a cosmic version of left-handedness written into the fabric of reality. What makes the axis of evil so unnerving isn't just the alignment itself, but what it implies about our place in the cosmos. For centuries, we've fought against the idea that we're special first, realizing Earth isn't the center of the solar system, then that our galaxy is one of countless others. Now, here's a phenomenon that whispers the opposite. Some primordial thread might connect the universe's birth to our own humble corner of it. Whether it's a measurement ghost, a statistical fluke, or a genuine crack in our understanding, one thing's certain: the universe hates coincidences. And this one's too big to ignore. We think we understand what the universe is made of until we run the numbers and realize we don't. Dark matter and dark energy dominate the cosmic budget, but even the ordinary matter we can detect, the protons, neutrons, and electrons that form planets, stars, and us, doesn't add up. In fact, about half of it has gone missing. This is the Barrian problem, and it's not some trivial accounting error. The discrepancy amounts to a staggering 40% of all normal matter that should be out there based on Big Bang nucleosynthesis calculations. So where did it all go? The hunt leads us to the emptiest places imaginable, the vast, thread-like structures between galaxies known as the cosmic web. Simulations show the universe's matter isn't randomly scattered. It's arranged in a delicate lattice of filaments, with galaxies clinging to the intersections like dew on a spiderweb. And hidden in those near-invisible strands, the warm, hot intergalactic medium, a diffuse, superheated plasma so thin it's practically a ghost. Here, temperatures soar to millions of degrees, but the gas is so sparse that a teaspoon of it would contain just a handful of atoms. That's the problem. This stuff is everywhere, but it's nearly impossible to see. Telescopes tuned to visible light pass right through it. X-ray observatories catch faint whispers, but only when the WIM clumps slightly around massive galaxy clusters. Even then, the signal is drowned out by cosmic noise. Imagine trying to spot a single lit match on Earth from the moon. That's the scale of the challenge. So astronomers get creative. Some look for the WIM's shadow, the way it subtly dims the light of distant quasars as their beams pass through. Others chase after the telltale distortions in the cosmic microwave background, where the WIM's electrons scatter ancient photons like fog bending a lighthouse beam. The stakes higher than you'd think. If the missing baryons are floating in these filaments, it confirms our models of large-scale structure. If not, we've overlooked something fundamental about how matter organizes itself across the cosmos. Either way, the hunt forces us to confront a humbling truth. The universe isn't just hiding its dark secrets. Even the ordinary stuff, the building blocks of everything we see and touch, can vanish into the cosmic background, leaving us to piece together reality from the faintest of echoes. Most nebulae in the cosmos swirl with organic, chaotic beauty, tendrils of gas twisting into celestial Rorschach tests. Then there's the red rectangle. Floating 2,300 light-years away in the constellation Monoceros, this cosmic oddity looks less like a stellar nursery and more like a piece of abstract art someone forgot in deep space. Its sharp, geometric lines form an almost perfect X-shape, encased in a rectangular halo so precise it seems engineered rather than born from natural forces. But the strangeness doesn't stop at its shape. This nebula glows with a deep crimson hue unlike anything else in the known universe, a color palette scientists still struggle to explain. At its heart lies a dying binary star system, HD 44179, where one star has already shed its outer layers, while its companion orbits so close it shapes the ejector into that uncanny angular structure. Think of it like two dancers spinning wildly, one flinging ribbons that wrap around both in a perfectly symmetrical pattern. But here's where the mystery deepens. The red rectangle's spectrum reveals spikes of light at very specific wavelengths, a signature that points to complex organic molecules called polycyclic aromatic hydrocarbons, or PAH. These carbon-rich compounds are common in space, but nowhere else do they emit such intense, focused red light. Some researchers speculate the binary star's unique radiation might be charging these molecules like a cosmic neon sign, while others argue the geometry itself. Those crisp cavity walls could be acting as a laser cavity, amplifying specific wavelengths. Then there's the dust. Most planetary nebulae disperse their material evenly, but the red rectangle's debris forms bizarre, ladder-like rungs between its X-shaped arms. One theory suggests magnetic fields, far stronger than expected, are sculpting these features. Another proposes that the dying star's pulses create shockwaves that stack dust in precise layers, like a 3D printer building steps in midair. But perhaps the most tantalizing clue lies in the nebula's symmetry. Nature abhors perfect geometry, yet here it is, a structure so balanced it feels intentional. Could this be a preview of our own sun's fate? In 5 billion years, when it becomes a red giant, might its death throes create something equally strange? Or is the red rectangle a cosmic fluke, a rare alignment of physics and chemistry we're lucky to witness? For now, it remains a dazzling enigma, a reminder that even in death, stars can defy expectations, leaving behind puzzles written in light and dust. Deep in the heart of our galaxy, an invisible menace might be lurking, a force capable of unleashing waves of destruction not just through space but across time itself. Galactic superwaves, theorized by physicist Paul Laviolette, are titanic tsunamis of cosmic rays erupting from the Milky Way's core in cycles of roughly 13,000 years. Picture this, the supermassive black hole at our galaxy's center, Sagittarius A, occasionally gorging on matter until it spews out a jet of high-energy particles so intense it could bathe the entire galactic disk in radiation. These aren't just gentle ripples, they're tsunamis of atomic nuclei accelerated to near light speed, powerful enough to strip atmospheres, trigger ice ages, and rewrite the genetic history of planets in their path. The evidence, layers of cosmic dust in ancient ice cores, show spikes in radioactive isotopes like beryllium-10, dating back to periods matching mass extinctions on Earth. Even more chilling, cave paintings from 12,000 years ago, around the time of the Younger Dryas climate catastrophe, depict what look like plumed serpents raining from the sky. Could these be primitive records of a superwave's fiery tendrils lighting up the atmosphere? Skeptics argue the timing could be coincidence, but the implications are undeniable. If these waves are real, we're long overdue for another, and modern civilization, with its delicate web of satellites and power grids, might be far more vulnerable than prehistoric species ever were. Now, shift your gaze from the galactic scale to the subatomic, and meet the particle that broke physics. On October 15, 1991, the University of Utah's Fly's Eye detector registered a cosmic ray unlike anything ever seen. Dubbed the "Oh my God" particle, this single proton hit Earth's atmosphere with the kinetic energy of a baseball traveling 60 miles per hour, all packed into a speck smaller than an atom. The math was incomprehensible. To reach such energies, this proton would need to outrace nature's speed limit, traveling at 99.999999999999996% of light speed. Even more baffling, we still can't explain where it came from. Potential sources like supernova or merging neutron stars fall laughably short of the required power. Only a handful of cosmic monsters could theoretically produce such energy-active galactic nuclei with jets screaming across millions of light years, or perhaps colliding galaxy clusters accelerating particles in their shockwaves. Yet none of these were lined up with the particle's trajectory when it struck. Some theorists whisper about exotic relics from the Big Bang, or defects in spacetime itself crumbling like a dying star and releasing pent-up energy. Then there's the unsettling possibility that our understanding of particle physics is incomplete, that at energies this extreme, the universe plays by rules we've yet to discover. What binds these two phenomena together isn't just raw power, but the humbling truth that the cosmos operates on scales we're only beginning to fathom. Whether it's galaxy-spanning waves that reset the clock of life, or lone particles carrying the punch of a pitcher's fastball, these mysteries force us to confront how little we know about the forces shaping our existence. And perhaps that's the most thrilling part, not the answers we've found, but the staggering questions still waiting in the dark. The cosmic microwave background should be a flawless tapestry of the early universe's heat, a nearly uniform glow with only the tiniest ripples. But there's one spot where that tapestry appears to have a tear, a chilling billion-light, year-wide cold spot in the constellation Eridanus, where temperatures dip inexplicably lower than anywhere else. This isn't just a minor statistical blip. It's a cosmic anomaly so vast and unexplained that some scientists wonder if we're staring at the fingerprint of another universe brushing against our own. First detected by NASA's WMAP satellite in 2004, then confirmed by the Planck mission, the Eridanus supervoid defies expectations. Cold spots aren't inherently unusual, random fluctuations occur, but one this large should be staggeringly rare, with odds around 1 in 50,000. At first, astronomers scrambled to find a more mundane explanation. Could it be an enormous void, a region of space nearly devoid of galaxies, where the lack of matter cools photons passing through it via the integrated Sachs-Wolf effect? That would make sense, except the void required to explain the temperature drop would need to be impossibly vast, far larger than any structure cosmologists thought possible. Then came the kicker. When teams scoured the Eridanus region for such a void, they found almost nothing. Surveys revealed underdense areas, sure, but nothing on the scale needed to account for the cold spot's depth. It's as if the universe handed us a receipt for a missing item we never purchased. This left theorists with two unsettling options. Either we've witnessed a statistical fluke so unlikely it calls into question our entire understanding of cosmic structure, or we're seeing something far stranger, evidence of a multiverse. Enter the multiverse hypothesis. If our universe is just one bubble in an infinite froth of others, perhaps the Eridanus cold spot marks where our bubble once collided with another. The energy released in such an impact could have left a bruise on spacetime, a region where the cosmic microwave background carries the echo of that ancient collision. It's a radical idea, but not without precedent. The same quantum field theories that explain inflation, the universe's explosive early growth, also predict such bubble universes popping into existence constantly. Yet skeptics push back. Maybe the void is there, just hidden behind observational limits. Or perhaps the cold spot is a rare but natural fluctuation, no more mysterious than rolling the same number on a die a dozen times in a row, unlikely but not impossible. Others suggest exotic physics, like dark energy interacting unevenly with matter, could mimic the effect. What makes the Eridanus supervoid so compelling isn't just the mystery itself, but what it represents, a crack in the facade of our cosmic models, a place where the universe whispers that its rulebook might have pages we've yet to read. Whether it's a statistical ghost, a hidden void, or a window into the multiverse, one thing's certain. In a cosmos that's supposed to make sense, this cold spot remains an icy reminder of how much we still don't understand. Somewhere above us right now, an object drifts silently through the darkness, an enigma wrapped in conspiracy theories, bad translations, and just enough truth to keep the mystery alive. This is the legend of the Black Knight satellite, a so-called alien probe allegedly orbiting Earth for thousands of years. But here's the twist. The truth behind this myth is far stranger than fiction, revealing just how easily misinformation can take root in the gaps of our understanding. The story begins with a kernel of reality. In 1998, astronauts aboard the space shuttle Endeavour spotted an unusual piece of debris during a mission, a thermal blanket that had torn loose from the spacecraft. But conspiracy theorists, seizing on grainy footage, claimed it was something far more sinister, an ancient alien satellite of unknown origin. From there, the myth snowballed. Claims surfaced that Nikola Tesla intercepted mysterious radio signals from this object in 1899. Others insisted it appeared in medieval paintings or was documented by the Knights Templar. The internet lit up with speculation, turning space junk into an interstellar Rosetta Stone. But let's dissect the facts. The Black Knight label itself stems from a mistranslation of Cold War era reports about Soviet satellites, while the infamous 13,000-year-old orbit claim traces back to a misread NAS, a press release about cosmic radiation dating. Even the supposed historical depictions crumble under scrutiny. What some call satellite silhouettes in Renaissance art are often just artistic flourishes or damaged paint. So why does the myth persist? It taps into a primal fascination with the idea that we're not alone, and that evidence of extraterrestrial contact has been hiding in plain sight all along. The irony, real unexplained objects do occasionally streak across our skies, like the interstellar visitor Oumuamua or the Pentagon-confirmed UAPs. But in a world hungry for mysteries, sometimes the most ordinary explanations, a lost blanket, a garbled translation morph into legends that outlast the truth. The Black Knight's legacy isn't just about aliens. It's a cautionary tale of how easily facts can warp when they collide with our desire for wonder. Because in the end, the universe is mysterious enough without inventing satellites that were never there. There's an ancient structure lurking in the distant cosmos so enormous it shouldn't exist, a galactic filament stretching 10 billion light-years from end to end. a behemoth that makes our local superclusters look like specks of dust. This is the Hercules-Corona Borealis Great Wall, the largest known structure in the observable universe, and its very existence throws a wrench into one of cosmology's most fundamental assumptions, that on large enough scales, the universe should look roughly the same in every direction. Discovered in 2013 by analyzing gamma-ray bursts, the death screams of massive stars, this cosmic leviathan defies the principle of homogeneity, the idea that matter should be evenly distributed when viewed across vast distances. Picture stirring cream into coffee until it's uniformly mixed. That's how cosmologists expected the universe to behave at scales beyond a few 100 million light-years. But the Great Wall shatters that expectation, presenting a sprawling network of galaxies and galaxy clusters so densely packed that it challenges how we understand the universe's large-scale structure. Here's what makes it so perplexing. According to standard cosmological models, structures this massive simply couldn't have formed in the time available since the Big Bang. Gravity works slowly, pulling matter together over eons, yet here we're seeing a filament nearly 1/10 the diameter of the observable universe, a structure that would have required more time to assemble than the cosmos has existed. Some theorists suggest alternative explanations, like exotic forms of dark energy that accelerated structure formation in the early universe. Others propose this might be evidence of a pre-Big Bang anomaly, a relic of some primordial fluctuation that seeded the wall's formation before time as we know it began. Then there's the unsettling possibility that we're misinterpreting what we're seeing. Gamma-ray bursts used to map the wall's outline might be misleading us if they're not perfectly tracing the underlying matter. Or perhaps the wall isn't a single coherent structure but a chance alignment of smaller filaments, like mistaking a tangle of separate spiderwebs for one colossal net. Yet even these caveats can't fully explain away the wall's staggering scale. What makes the Hercules-Corona Borealis Great Wall more than just a record-breaking curiosity is what it implies about the limits of our cosmic maps. If structures this vast exist, how many others might we have missed? And if the universe isn't as uniform as we thought, what does that mean for our understanding of its birth, evolution, and ultimate fate? The wall stands as a silent challenge to cosmology, a reminder that even our grandest theories must bend when faced with the universe's unyielding contradictions. On the rusty plains of Mars, a gas is playing hide and seek with our robots, and the stakes couldn't be higher. Methane, a molecule often tied to life on Earth, keeps appearing and vanishing in the Martian atmosphere in ways that defy easy explanation. NASA Curiosity rover has detected sudden spikes of methane, sometimes 10 times background levels, only for the gas to dissipate within hours. These erratic pulses have scientists torn between two electrifying possibilities. Is this the whisper of subterranean microbes, or just geology trolling us with false hope? The plot thickens when you compare orbital data with ground measurements. ESA's Trace Gas Orbiter, equipped with state-of-the-art spectrometers, has repeatedly failed to confirm Curiosity's methane spikes from above. At first glance, this seems like a sensor disagreement until you realize the timing might hold the key. Methane on Mars appears to follow a diurnal cycle, peaking at night and vanishing by day. Some theorize the gas gets destroyed by ultraviolet radiation at sunrise, while others suggest it's seeping from underground reservoirs only to be broken down by reactive surface minerals before satellites can spot it. Then there's the question of origin. On Earth, over 90% of atmospheric methane comes from biological sources: cows, wetlands, even termites. But Mars offers non-biological pathways too, a process called serpentinization, where water interacts with olivine-rich rocks, can produce methane abiotically. The problem: current models suggest serpentinization alone can't explain the rapid, localized bursts Curiosity has sniffed out. Even more intriguing, Some methane plumes correlate with seasonal changes, rising during warmer months like clockwork, a pattern that, on our planet, would scream biological activity. The European Space Agency's Mars Express orbiter added fuel to the fire when it detected one of the largest methane releases ever recorded, a cloud containing nearly 21,000 tons of the gas. If purely geological, what subterranean process could unleash such a concentrated burst? Underground aquifers reacting with volcanic heat, ancient methane clathrates thawing after eons, or the possibility that quickens pulses microbial colonies breathing beneath the permafrost. What makes this mystery so maddening is the duality of methane itself. It's both a biosignature and a geochemical red herring, a molecule that could rewrite textbooks either way. Future missions like NASA Mars Life Explorer, designed to drill deeper than ever before, may finally settle the debate. Until then, Mars keeps its secrets close, teasing us with whiffs of gas that could mean everything or nothing at all. At the North Pole of Saturn, a storm rages unlike anything else in our solar system, a perfect six-sided hexagon large enough to swallow 4 Earths. This isn't some fleeting atmospheric quirk. It's been spinning relentlessly for at least 40 years, since Voyager first glimpsed it in the early 1980s, and possibly much longer. Wrapped in swirling bands of yellow and gold, this geometric behemoth defies everything we know about fluid dynamics because storms don't form straight edges. Yet there it is, a cosmic honeycomb etched into the clouds, pulsing with winds that scream past at over 300 miles per hour. So how does a gas giant, a world without solid continents or mountain ranges to disrupt airflow, create something so precise? The leading theory takes us into the realm of standing wave patterns. Picture water swirling in a bathtub drain, forming small, temporary geometric shapes as it spins. On Saturn, the jet stream at the North Pole might behave similarly, with atmospheric currents moving at different speeds, creating a stable, hexagonal oscillation. Computer models suggest that if you rotate a fluid at just the right velocity under the right conditions, polygons can emerge naturally, like a cosmic experiment in fluid physics playing out on a planetary scale. But here's the catch: Earth's atmosphere doesn't do this. Our polar vortices, while powerful, are messy, circular affairs. The difference lies in the ingredients. Saturn's upper atmosphere is dominated by hydrogen and helium, fluids with low viscosity that can behave more like a single, coherent mass. Earth's thicker, nitrogen-rich air, combined with the disruptive influence of landmasses and oceans, breaks up any chance of such geometric purity. It's the difference between spinning a glass of water and a cup of syrup. One flows smoothly, the other resists. Yet even this explanation feels incomplete. Why 6 sides? Why not a pentagon or an octagon? Some researchers point to Saturn's deep internal heat, which might drive convective currents that reinforce the hexagon structure. Others speculate about the planet's unique magnetic field, which could be interacting with charged particles in the atmosphere to stabilize the shape. Then there's the bizarre fact that the hexagon seems to change color with Saturn's seasons, shifting from golden hues to bluish tones as sunlight angles shift over its 30-year orbit. The most haunting possibility: this storm might be older than recorded human history. Without solid surfaces to sap its energy, Saturn's hexagonal vortex could have been spinning for millennia, a near-eternal monument to the chaos and order woven into the fabric of gas giants. It's a reminder that even in a universe governed by universal laws, there's always room for the inexplicable, a shape that shouldn't exist, dancing in the clouds of a world we're only beginning to understand. Beyond the orbit of Neptune, where sunlight is just a faint glimmer, thousands of icy bodies circle the Sun in a vast donut-shaped region called the Kuiper Belt. This frozen frontier should teem with objects gradually thinning out as you go farther, except it doesn't. Instead, astronomers have stumbled upon a cosmic drop-off so abrupt it's been dubbed the Kuiper Cliff. Around 50 astronomical units from the Sun, that's 50 times Earth's distance, the number of detectable objects plunges sharply, as if someone drew a line in the solar system's dust and said, "No further." This isn't just a curiosity. The Kuiper Belt's sudden edge defies decades of solar system formation models, which predict a smooth, tapering distribution of icy debris. One explanation points to an unseen gravitational bully, a hypothetical planet 9 lurking in the darkness. This elusive world, estimated to be 5 to 10 times Earth's mass, could have shepherded objects into clustered orbits while clearing out others, creating the observed cliff. The math is compelling. Simulations show such a planet could explain not just the Kuiper Cliff, but also the bizarre, tilted orbits of some distant objects like Sedna. Yet after years of searching, no telescope has spotted this phantom planet, leaving astronomers to wonder if it's hiding in plain sight or if we're chasing a celestial mirage. But Planet 9 isn't the only suspect. Some argue the cliff might be an illusion, a trick of observational bias. Detecting dim, distant Kuiper Belt objects is like trying to spot a single candle flame from 1,000 miles away. Current surveys might simply be missing fainter objects beyond 50O, creating the false impression of a void. Yet even this explanation feels shaky. Advanced telescopes like Subaru and the upcoming Vera Rubin Observatory should have glimpsed at least some outliers if they existed. The fact that they haven't suggests the drop-off might be real, and that's where things get truly weird. Alternative theories veer into cosmic archaeology. Perhaps the Kuiper Cliff marks the outer edge of our Sun's primordial birth cluster, a relic from when the solar system formed alongside sibling stars in a dense stellar nursery. The gravitational tug of these long-lost siblings could have stripped away objects beyond a certain boundary, leaving a fossilized edge. Or maybe the cliff is evidence of a rogue planet's ancient passage, a celestial intruder that plowed through the Kuiper Belt billions of years ago, scattering debris like a bowling ball crashing through pins. The Kuiper Cliff isn't just a boundary, it's a crime scene, and we're still dusting for fingerprints. Every unexplained orbit, every missing object is a clue pointing to forces we've yet to understand. Whether it's an unseen world, a ghostly stellar encounter, or something even stranger, this icy frontier holds secrets that could rewrite the story of our solar system's birth and the violent processes that shaped it. Galaxies are supposed to be held together by dark matter, an invisible scaffold that keeps stars from flying apart. That's what every model tells us. But then there's NGC 1052 DF2, a bizarre ghost of a galaxy that seems to play by its own rules. Discovered in 2018, this ultra-diffuse galaxy floats in the constellation Cetus like a cosmic rebel, flaunting a secret. It appears to have no dark matter at all. At first glance, DF2 looks unremarkable, a wispy, translucent collection of stars so sparse you could practically see straight through it. But when astronomers measured its rotation speeds, expecting the telltale tug of dark matter's gravity, they got silence. The stars moved exactly as Newton's laws predict for visible matter alone, as if the universe forgot to sprinkle in the dark stuff. This wasn't just a minor discrepancy, it was like weighing a bag of feathers and finding it as heavy as lead. Either our tools were broken or our understanding of how galaxies form had a glaring hole. Skeptics pounced. Maybe we miscalculated DF2's distance, throwing off mass estimates. Or perhaps its stars trace unusual orbits that mimic a dark matter-free profile. Some suggested tidal forces from a neighboring galaxy stripped its dark matter away, though there's no obvious culprit nearby. But the most compelling counter-evidence came from DF2's globular clusters, dense swarms of ancient stars orbiting the galaxy. These clusters were bizarrely massive, 10 times heavier than typical ones, yet their motions also showed no dark matter influence. It's as if the galaxy and its clusters conspired to break the rules together. Then came the plot twist. In 2021, a team reanalyzed DF2's distance using Hubble data and claimed we'd gotten it wrong. It was actually closer, meaning its visible mass might suffice to hold itself together after all. But this just deepened the mystery. If DF2 does have dark matter, its distribution defies all models, clustering in ways we've never seen. The implications are staggering. If dark matter isn't universal, we might need entirely new physics to explain why some galaxies cling to it while others shun it. Or worse, what if DF2 isn't an outlier, but a sign that dark matter behaves in ways we haven't imagined, clumping unevenly across the cosmos? For now, this faint smudge of stars stands as a cosmic paradox, daring us to rethink one of astronomy's most fundamental assumptions. Whether it's a measurement glitch or a revolution in the making, one thing's clear: the universe loves throwing curveballs, and DF2 might be its sneakiest pitch yet. Black holes come in two familiar flavors: stellar mass remnants of collapsed stars and supermassive behemoths anchoring galaxies. But nestled in the constellation Monoceros, just 1,500 light-years away, lurks a cosmic runt that defies this binary, the unicorn. Weighing in at a mere 3 times the Sun's mass, this pint-sized singularity isn't just a curiosity, it's a missing link in the black hole family tree, dangling tantalizingly close to the theoretical edge of what can even become a black hole. Detecting something this small is like trying to spot a marble in a snowstorm from a mile away. Traditional methods hunting for X-rays emitted by heated infalling gas failed completely because the unicorn is too lightweight to rip apart its companion star violently enough to produce that telltale glow. Instead, astronomers had to get creative. They noticed the companion star, a red giant, wobbling subtly as if tugged by an unseen force. Its light also dimmed periodically, suggesting something compact, too small to be a star, too dark to be anything but a black hole, was passing in front. This backdoor detection method opened a new window onto the elusive population of quiet black holes that might be hiding in plain sight all around us. But why does size matter? The unicorn sits squarely in the so-called mass gap, the mysterious no-man's land between the heaviest neutron stars around 2.2 solar masses and the lightest known black holes around 5 solar masses. Theory predicts collapsing stars should produce black holes across this range, yet until now we'd found almost none. Some physicists argue this gap reveals a fundamental limit of stellar collapse. Perhaps neutron stars resist becoming black holes until they've packed on extra mass through mergers or accretion. Others speculate we've been looking wrong, missing legions of these shy, lightweight black holes because they don't scream their presence with X-ray flares. The implications ripple across astrophysics. If the unicorn isn't alone, our galaxy could be teeming with similar hidden black holes, rewriting estimates of how many stellar corpses lurk in the darkness. Their existence might also explain puzzling gravitational wave signals from mergers that don't quite fit known categories. Even more intriguing, some ultralight black holes could be primordial, not born from stars at all, but forged in the seething chaos of the Big Bang itself, making them cosmic fossils from the universe's first seconds. For now, the unicorn remains an enigma wrapped in gravitational whispers. Its very presence forces us to reconsider how stars live, die, and cross the threshold into darkness. And if this faint ghost in Monoceros is any indication, the cosmos might be hiding far more surprises on the featherweight end of the cosmic scale. Black holes so small, so stealthy, they've been dancing just beyond our gaze all along. In 2020, astronomers scanning the sky with radio telescopes stumbled upon something so bizarre it was initially dismissed as a software glitch. Massive, perfectly circular rings of radio emission hanging in space like cosmic smoke rings, some wider than entire galaxies. These odd radio circles, or ORC, have no visible counterpart in optical, infrared, or X-ray light. They just are ghostly halos of energy with no obvious source, no central engine, and a symmetry so precise it's left researchers grasping for explanations that don't involve Star Trek-level tech. The first ORC, nicknamed ORC-1, was discovered in archival data from Australia's ASCAP radio telescope. Since then, fewer than a dozen have been identified, each spanning hundreds of thousands of light years. What makes them even stranger is their structure. Unlike the chaotic remnants of supernova or the twisted jets of active galaxies, ORCs are uncannily smooth, like ripples from a stone dropped in a pond, except there's no stone. One leading theory suggests they're shock waves from an ancient cataclysmic event, perhaps two supermassive black holes merging at the heart of a galaxy, releasing a spherical tsunami of energy that's still expanding outward. The problem: no galaxy at the center of these rings shows signs of such a violent past. Another hypothesis points to starburst galaxies, where frenetic star formation generates galactic winds powerful enough to blow bubbles in intergalactic gas. But ORCs are far larger and more symmetrical than any known wind-blown structures. Then there's the dark horse theory: dead radio galaxies. Some galaxies once hosted blazing quasars whose jets have long since shut off, but their old, faded lobes might still glow faintly in radio waves. Yet even this fails to explain the ORCs' perfect circularity. Active galactic nuclei produce messy, twin-jet structures, not pristine rings. The most tantalizing and unsettling idea involves something entirely new. Could ORCs be the imprint of wormholes, their mouths funneling particles into a torus of radiation? Or perhaps they're cosmic scars from collisions between bubble universes in a multiverse? While these notions veer into speculative territory, they highlight just how thoroughly ORCs defy conventional astrophysics. What's certain is that these enigmatic circles are rewriting the rules of what we thought possible. They're not explosions, they're not echoes, they're something else entirely, a phenomenon lurking in plain sight, waiting for us to crack the code. And with each new detection, the universe seems to be teasing us. For all our telescopes and supercomputers, some mysteries still refuse to fit inside the boxes we've built for them. Somewhere beyond the edges of our cosmic maps, a force is pulling entire galaxy clusters toward the unknown. This isn't just random motion, it's a coordinated march, a current of galaxies all streaming in the same direction at over 2 million miles per hour, as if drawn by some unseen cosmic magnet. Astronomers call it the dark flow, and it's one of the most unsettling discoveries in modern cosmology because, by all accounts, it shouldn't exist. The story starts with the cosmic microwave background, the afterglow of the Big Bang. In 2008, a team analyzing data from NASA's Wilkinson Microwave Anisotropy probe noticed something bizarre. The CMB isn't perfectly uniform. Its slight temperature variations reveal how matter was moving in the early universe. But here's the shocker: hundreds of galaxy clusters appeared to be drifting together, their motion imprinted like fingerprints on the CMB's heat map. This wasn't just a gentle tug, it was a full-blown exodus, with clusters racing toward a point in the sky near the constellations Centaurus and Vela. What could possibly exert such a pull? The disturbing answer: nothing in our observable universe. The sheer scale of this motion rules out known superclusters or dense regions of dark matter. Even the Shapley Attractor, the largest concentration of mass we've mapped, can't account for it. The only explanation that fits is something beyond our cosmic horizon, structures so massive they warp spacetime on scales we can't see, their gravity reaching across the void to tug at everything in their path. That's where things get truly mind-bending. If these phantom attractors exist, they might be evidence of other universes. In the multiverse theory, our cosmos could be one bubble in an infinite froth of others, each with its own physical laws. Where these bubbles press against each other, their gravitational influence might leak through, creating the cosmic currents we see. It's like standing on a beach, feeling the tide pull at your feet, and realizing the waves come from an ocean you'll never see. Skeptics argue the dark flow could be a statistical illusion, an artifact of how we measure galaxy motions or interpret the CMB. Others suggest our models of large-scale structure are incomplete, missing hidden mass distributions. But each new study, including analyses from the Planck satellite, seems to confirm the flow's reality while deepening its mystery. The implications are staggering. If the dark flow is real, it means our universe isn't just expanding, it's being reshaped by forces from beyond the edges of existence. Whether it's a flaw in our measurements, a gap in our theories, or a window into the multiverse, one thing's clear: the cosmos still holds currents we're only beginning to fathom, flowing toward answers we can't yet imagine. When a star goes supernova, it's supposed to be a one-way ticket to cosmic oblivion, a catastrophic explosion that obliterates the star completely. But in 2012, astronomers witnessed something that shouldn't exist, a star that refused to die. SN 2012Z, a so-called zombie star, did the impossible. It survived its own supernova, lingering in the aftermath like a cosmic ghost. This wasn't just a fluke. It was the smoking gun for a bizarre class of stellar explosions called Type IX supernova, events so strangely feeble they barely deserve the supernova name, yet they're rewriting our understanding of how stars die. What makes these explosions different? Picture a typical Type Ia supernova, the kind we use to measure cosmic distances. A white dwarf, the dense core of a dead star, steals matter from a companion until it hits a critical mass, triggering a runaway nuclear explosion that vaporizes it completely. Type IX events follow the same script until they don't. Instead of annihilating the star, the explosion fizzles partway through like a firework that only half detonates. The outer layers blast away, but the core remains scorched, battered, but still intact. It's the difference between a building collapsing into dust versus one that loses its upper floors but keeps its foundation. The zombie star SN 2012Z gave us the first clear proof of this survival. Hubble Space Telescope images taken before the explosion showed its progenitor system, a white dwarf siphoning gas from a helium-rich companion. Post-explosion images revealed something astonishing. Not just the fading supernova, but the surviving star itself, shining defiantly amid the wreckage. Follow-up studies found it was still there years later, a celestial phoenix that outlasted its own death throes. Why does this matter? Because Type IX events are the universe's way of showing us stellar physics has a gray area. Some models suggest these partial explosions happen when the white dwarf's ignition starts at multiple points simultaneously, creating a weaker, asymmetric detonation. Others propose the star's rapid spin or unusual composition acts like a cosmic circuit breaker, stopping the explosion prematurely. Whatever the cause, the implications are profound. If white dwarfs can survive supernova, even partially, our estimates of how often these events occur and how much heavy elements they spread through the cosmos might need serious revision. But the biggest mystery remains: what happens to these undead stars afterward? Do they slowly cool into darkness, forever scarred by their near-death experience? Or could they, against all odds, refuel from their companions and explode again? The universe loves its second acts, and in the case of zombie stars, we might just be witnessing the first chapter of a story we never knew existed. Most planets orbit their stars like clockwork, with paths aligned to the same flat plane as their stars spin. But KOI 5 AB didn't get the memo. Floating 1,600 light-years away in the constellation Cygnus, this gas giant has the cosmic audacity to dance to its own rhythm, orbiting at a near-perpendicular angle to not one, not two, but three parent stars. It's the gravitational equivalent of a rebellious teen flipping the rules upside down, and its existence has astronomers questioning everything we thought we knew about how planets form in multi-star systems. Discovered by NASA Kepler mission in 2009, KOI 5 AB was initially overshadowed by simpler finds, until follow-up observations revealed its bizarre setup. The system's primary star, Koi 5a, hosts the planet while two companion stars, Koi 5b and Koi 5c, circle each other farther out. Normally, all three stars and their planets should share roughly the same orbital plane, like flat plates stacked neatly in a cupboard. Yet KY5Ab's orbit is tilted a jaw, dropping 50 degrees relative to its star's shared plane, making it the first known misaligned planet in a triple-star system. So how does a planet end up so dramatically off-kilter? One theory points to cosmic chaos during its infancy. Imagine the system's stars playing gravitational tug-of-war, their competing pulls yanking the protoplanetary disk, the swirling ring of gas and dust where planets form, into a warped, tilted orientation. Alternatively, KY5Ab might have been born normally, only to be violently knocked askew by a close encounter with another star or rogue planet. Some models even suggest the two outer stars' gravitational punches could have torqued the planet's orbit over millions of years, like a spinning top wobbling under invisible forces. But here's the real kicker: KY5Ab shouldn't exist at all. Multi-star systems were already considered hostile environments for planet formation, their complex gravity fields prone to tearing apart nascent worlds. Yet this defiant planet not only survived, it thrived, carving out a stable orbit in a celestial minefield. Its resilience hints at a hidden diversity of planetary systems far stranger than our own, where planets might spiral around stars in wild, unpredictable paths. The discovery forces us to confront the gaps in our theories. If misaligned planets like KY5Ab are common, it means the universe has a flair for the unexpected, crafting worlds in ways we've yet to imagine. Future telescopes like the James Webb Space Telescope could analyze similar systems for clues, searching for chemical fingerprints that reveal how these cosmic misfits came to be. Until then, KY5Ab stands as a cosmic iconoclast, a reminder that even in the ordered symphony of the cosmos, there's always room for a little anarchy. The James Webb Space Telescope was designed to peer into the cosmic dawn, the first chapters of the universe's story. But instead of filling in gentle details, it's handed us a paradox. What astronomers expected to find were infant galaxies, frail and flickering in the early universe's twilight. What they actually discovered were cosmic titans fully formed, massive galaxies swirling in the darkness barely 300 million years after the Big Bang. That's like finding a skyscraper in the middle of the Stone Age. These galaxies, labeled universe breakers by stunned researchers, shouldn't exist. Not under our current understanding of cosmic evolution, and their existence is forcing us to confront an uncomfortable question. Is our entire timeline of galaxy formation wrong, or are we staring at evidence of physics we've never seen before? Take Sears 93316, for example, a galaxy so distant its light has traveled 13.4 billion years to reach us. Under normal models, a galaxy that old should be small, maybe a few scraggly clusters of stars clinging together. Instead, it's a behemoth with hundreds of billions of solar masses, as hefty as our own Milky Way, but existing when the universe was just a toddler. Simulations suggest galaxies this massive would need nearly 1 billion years to form, yet here they are, fully grown before the universe even hit its 300 millionth birthday. It's as if a human baby were born already able to sprint a marathon. So what's going on? One camp argues we're witnessing flaws in our models, not the universe. Perhaps early stars formed far more efficiently than we thought, converting gas into suns at breakneck speeds. Or maybe dark matter, the invisible scaffolding of galaxies, clumped together faster in the primordial universe, accelerating galaxy growth. But even these tweaks feel like band-aids on a gaping wound. The numbers just don't add up. Then there's the more radical possibility: we're seeing hints of exotic physics. Some theorists whisper about primordial black holes, tiny, ancient singularities born in the Big Bang's first seconds, acting as seeds for supercharged galaxy formation. Others speculate about modifications to gravity itself, with Einstein's equations bending differently in the early universe's extreme conditions, the wildest idea. These galaxies aren't young at all, but relics from a previous cosmic cycle evidence our universe didn't start with the Big Bang, but rebounded from something before it. The irony is rich. JWST was built to confirm our theories, not shatter them. Yet every time it peers deeper, it finds the impossible staring back. These galaxies aren't just rewriting a few footnotes in cosmology, they're tearing whole chapters out of the book. Whether the answer lies in flawed models, new physics, or something even stranger, one thing's clear: the early universe was far more creative than we ever imagined. And somewhere in that chaos of ancient light, the real story of cosmic dawn is waiting to be told. Out in the cosmic deep field, where the James Webb Space Telescope peers back to the universe's infancy, a storm is brewing, not among the stars but among the scientists studying them. The prevailing wisdom said the first galaxies should be small, fragile things, barely holding themselves together in the turbulent aftermath of the Big Bang. Instead, JWST has handed us galaxies that look like they've had 1 billion years to bulk up, flaunting mature spirals and massive star clusters when the cosmos was barely old enough to crawl. Take Glass Z13, for instance, a galaxy so ancient its light comes from just 300 million years after creation, yet it's already churning out stars at a rate that defies every simulation we've run. Now, the real tension isn't just that these galaxies exist, it's what they force us to confront. On one side, traditionalists argue we might be misreading the data. Could dust in the early universe be reddening these galaxies, making them seem older and further away than they are? Or might errors in calibration be distorting their apparent brightness, tricking us into overestimating their mass? These are fair critiques, but here's the rub: even accounting for these factors, the numbers still don't square. Adjust the models all you want, and these cosmic early bloomers still loom too large too soon. That's where the radical ideas kick in. Some theorists are flirting with modifications to gravity itself, suggesting Einstein's equations might need tweaking under the extreme densities of the young cosmos. Imagine if, in those first fiery eons, gravity worked slightly differently, stronger in certain pockets, accelerating the collapse of gas into stars at rates we wouldn't predict today. Others point to dark matter behaving in unexpected ways. Perhaps it clumped faster than we thought, forming dense seeds that pulled in ordinary matter like cosmic magnets. Then there's the wild card: what if these galaxies didn't form from scratch at all? A fringe but fascinating idea posits they're remnants of a previous universe, recycled through a big bounce. A hypothetical scenario where our cosmos emerged from the collapse of an earlier one. It's a long shot, but when faced with galaxies that look like they've lived a lifetime before time itself should have allowed, even the wildest guesses start feeling plausible. JWST discoveries aren't just rewriting a chapter in astronomy, they're threatening to tear the whole book apart. Whether it's flawed models, new physics, or something even stranger, one thing's undeniable: the universe's opening act was far more dramatic than we ever imagined. And with every new observation, the telescope isn't just showing us the past, it's revealing how much we still don't know. From vanishing stars to zombie suns, from galactic ghosts to invisible rivers of dark matter pulling at the fabric of reality, we've journeyed through 30 of the cosmos' most baffling enigmas, and yet we've barely scratched the surface. Each one of these phenomena is a humbling reminder: for all our telescopes, equations, and ingenuity, the universe operates on a scale that still leaves us wide-eyed. The wow signal's fleeting whisper, the red rectangle's impossible geometry, Saturn's hexagon spinning like a celestial gear, these aren't just puzzles waiting to be solved. They're cosmic breadcrumbs leading us deeper into the unknown, where every answer unravels 10 new questions. Think about it. We live in a reality where black holes might be holograms, where entire galaxies spin without dark matter, where ancient light carries the fingerprints of other universes. The more we learn, the clearer it becomes. The universe isn't just stranger than we think, it's stranger than we can think, and that's the real magic. Because in these gaps of understanding, in these edges of the map where science meets speculation, there's room for wonder, for reinvention, for the thrilling possibility that the next big discovery might upend everything we thought we knew. So here's to the mysteries, the ones we've named, and the countless others lurking in the dark. To the researchers chasing shadows, the dreamers rewriting textbooks, and yes, to you, staring up at the night sky and wondering what else is out there. Because curiosity isn't just a trait, it's our compass in the cosmos. Now it's your turn. Which of these phenomena left you speechless? Drop your favorite in the comments, and let's keep the conversation as infinite as the universe itself. After all, the greatest discovery hasn't been made yet, and who knows, the next clue might be hiding in